All right. Guidelines for solving related rate problems. So we kind of set the narrative yesterday for today. I just want to say that because Ms. Weezer Matthews always said we got to set the narrative. All right. Identify all quantities and quantities to be determined. Make a sketch and label the quantities. Write an equation involving the variables whose rates of change are either given or to be determined. Use chain rule implicitly. Differentiate both sides with respect to time. That's going to be the big thing today. There's a couple other things that really help. After completing step 3, substitute into the resulting equation all known values for the variable and the rates of change and solve for the required equation. So those are the things that you really don't need to memorize the steps, you just need to understand the process. Understand the way that you're going to tackle a problem. So what I always do first, let's read. We're going to read through the problem. I just read the problem. I don't do anything but just read it one time just to read it and see if I can get the context. All right, so find the rate of change of the distance between the origin and a moving point on the graph of y equals x squared plus 1 if dx dt is equal to 2 centimeters per second. So let's think about the context of the problem. Okay, what I picked up on there is that there is a point on a graph and it's moving, and the distance between that point and the origin is changing. So let's just draw a picture here, and then we'll start writing down the quantities that are given and the quantities to be determined. So I'm going to draw this. I can draw this. I'm actually good at this kind of drawing. I can draw a graph. What does y equals x squared plus 1 look like? So we have this parabola. Shift it up 1. We'll go into deeper understanding of what we're being asked to do here in a second. Let's just get the context down. So we have this parabola, and it has a point on it that's moving. Okay, little ADD guy. All right, so we have this little point that just can't stay still. It's moving, and it's a certain distance away from the origin, so we know where the origin's at. And so let's imagine that distance there. So find the rate of change of the distance between the origin and a moving point on the graph. So we know there's a distance between the origin and some point that's moving on the graph, and that as that point moves, what happens to that distance between that point and the origin? It's changing. Sometimes it's getting what? Sometimes it's getting smaller, sometimes it's getting bigger. It depends on where it's at. As it moves towards the y-axis, it's getting smaller. Then as it moves away from the y-axis, it'll get bigger. That distance between the origin and that point. So you know what the context of the problem is at least. Now let's talk about actually related rates. There are some variables here. Okay, let's talk about the variables. Okay, first of all, there is the distance between the origin and that point. So let's give it a name. What do you want to call the distance between the origin and that point? Don't use x or y because we're going to use that for something else. Huh? I use z. I like z. You could use delta. You could use whatever you want. I think z makes sense. Some people use d. I kind of stay away from d because we're using d for derivative already. So a lot of times in physics they use z for distance.
If we're drawing, if we have to draw that on the calc exam, do we have to say
They don't care what you label, and they don't care what you do, and they're probably not even going to look at your drawing. Okay, that's for you more than them. So I'm going to label it z. You could certainly use something else. Some people said r because r is kind of related to what we did with right triangles when we did an x, y, and r. And we're going to do that in a minute anyways. So z is good. I like z. There's some other variables. You may tell me, as we think about a point, what variables does a point have? Well, if you imagine this altitude straight down, you know that there's an x distance and there's a y distance. So we've got a couple of different variables. We've got an x, we've got a y, we've got an r, we've got a z. Z is the distance between the origin and the moving point. X represents the distance of that point, moving point away from the origin, and y, horizontal distance. And y represents the vertical distance of that point away from the origin. Okay? So whatever your y value is, that's how far it is from the x-axis. Whatever your x value is, that's how far it is from the y-axis. Which again is always the origin. All right, now let's go ahead and go back to step 1 and let's talk about how we do a related rate problem. So we've got a sketch. We understand the context of the problem. We kind of get what they're asking. But without calculus, it seems like, well, I don't really know how I'd ever do this before calculus. How would you figure out how quickly the distance is changing? Well, that's where calculus steps in. All right, identify all quantities and quantities to be determined. Okay, Let's go back to the problem. Find the rate of change of the distance. All right? Is that one that we know or want to determine? Say it again. Find the rate of change of the distance. Is that one do we know or want to determine? That's one we want to figure out. And what did I say about rate yesterday? I had you underline it. What does rate mean? Come on, I said it yesterday. Rate, you need to know rate means derivative, just like slope means derivative now. Everybody, slope and rate just mean what now? Derivative. Because we're not talking about an average rate of change anymore. That was so ninth grade. Okay, we're talking about instantaneous rate of change. We're not talking about slope like we did in ninth grade where it was the slope of the secant. No, we're talking about slope of the tangent, which is instantaneous rate of change. We don't care about average anymore. And we want average, we'll go be average and be in ninth grade again. We are not average anymore. You are the high power, top of the food chain students at Perham High School now, okay? You talk about instantaneous rate of change and don't let anybody bother you about it, okay? So, find the rate of change of the distance. So which derivative am I interested in? Am I interested in the derivative for x? Am I interested in the derivative for y? Or am I interested in the derivative for z? I am interested in the derivative for z, the distance. That's what we let z be. Z is the distance between the origin and that moving point. Okay, little ADD guy. All right, so z is that distance. So if I want to represent the rate of change for distance, I need to say, I could call it z prime, but I told you to shy away from that. So how are we going to do this? We're not going to call it z prime. We're going to call it something. dz dt. Wow, you remembered, because today we're going to do everything with respect to what? Time. Everything's with respect to time when we do related rate problems. So I want to find, write that down. I want to find dz dt. That's the one I want to know. There you go, buddy. I want to know. You got to go again? You better watch this one. I want to know dz dt. That's the one I'm trying to find. Okay? And I want to know the distance between the origin and the moving point, which again we represented with z. On the graph of y equals x squared plus 1, nothing new there. If dx dt is 2 centimeters per second. So is that a given or an unknown? Yeah, that's given. So dx dt is equal to what? 2 centimeters per second. You do need to keep up with units on the AP exam. They do get points for units. On a free response problem, they only give 1 point for units, and you have to get the units right in every part to get that 1 point. If you screw it up one place, it's done, over. Kabosh. Okay? Hasta luego. Dead. See you later. Something. Alright, so I'm looking for dz dt. I know dx dt. There's another rate of change that we have. By the way, dx dt, let me explain what that means. That means if my point is, let's say this is at 1. If I move to the right, 1 second later, I'd be where? Look at it. If I label the x-axis in centimeters, and I'm at 1 centimeter, let's just pretend I'm at 1. I'm not, but let's just pretend I'm at 1. In fact, I don't know where I'm at because he's an ADD little guy. Okay, so if I'm at 1 and I go to the right, where would I be 1 second later? At 3. Another second later, I'd be at? Another second later? So every second it goes 2 centimeters. If I go to the left, if I'm at 1 right now, if I go to the left, where would I be a second later? -1. Another second later? -3. So it's the horizontal distance we're talking about. The horizontal distance changes 2 centimeters per second. So as I move every second, that point, its x value is going to change 2 centimeters along the x-axis every second. Now, that's assuming it's constant. Here's the thing I know about related rates. The rates aren't always constant. The rates can change. When you get into the balloon example, and we'll talk about it in a minute, you'll see that, and I think most of you will get that. They'll usually tell you, and you'll be able to figure it out in context of the problem. Just think about it. Some of it's common sense. Some of it's you have to be told. Some of it you just have to think about it. All right, there's another rate out there, dy dt. Let me talk about dy dt. dy dt is interesting because did they tell us dy dt? So it's unknown. Did they ask you to find dy dt? If they don't tell it and they don't ask for it, you don't want it. So dy dt is going to be a problem because I don't want it. I don't know it, and they don't ask for it. That's probably the biggest struggle with related breakdowns. If you can keep up with what's given and what you're trying to find, and if there's anything that else is out there that is a rate, but you're not interested in it, you've got to find a way to eliminate it. So if dy dt happens to pop up somewhere, I've got to eliminate it because I'm not interested in it. I don't have enough information, and they're not even asking for it, so why find something if you're not being asked for it? Okay, now we'll talk about how we're going to get that in a minute. So, all right, so this is the one we're after, and this is the one that we know. All right, step 2, write an equation. By the way, we're done with step 1. We understand the problem. We've got everything labeled. We understand that if we get a dy dt, we don't really want that one. So we're going to have to find a way to eliminate it. Write an equation that involves the variables whose rates of change either are given or are to be determined. Now, I want you to look at our diagram. This is why a sketch is so important. So think about it. You got an x and a z. Can anybody think of an equation that relates x and z? Any equation that you know in mathematics since 7th grade, geometry, anything.
X squared plus y squared equals z squared.
Exactly. That's the only one I can think of. Some people will say you could do trig equations, but the problem with trig equations, you'd have to bring in a theta. I don't know anything about angles. They haven't even mentioned an angle here, so I don't know if I'd go trig. I definitely can go the x squared plus y squared equals z squared route. Now let me go ahead and talk about that. If you're going to do x squared plus y squared equals z squared, which I do agree with, that is the equation that we're actually going to use, because you got to find that equation that relates x and z. Does this relate x to z? But can anybody tell me what the problem with this equation is? It has a y in it. So we're going to have to eliminate that y before we do anything with derivatives. Okay, so we'll talk about that in a second. But before I do anything else, since we got x squared equals y squared plus z squared, since we're talking about distance and we're wanting to find the rate of change for distance, we might as well go ahead and solve for distance here and actually change it from Pythagorean theorem to the distance formula. How can I solve for the distance? Come on.
Distance being z.
Huh?
Distance being z.
Yeah, distance z, because that's what we said it was.
So root x.
Yeah, just square root it. So we'd have actually z equals the square root of x squared plus y squared. Can anybody tell me why I did not put a plus or minus? Because usually I would.
Because they're both squared, so they have to be positive, right?
No, because the plus or minus would come outside the square root, so that wouldn't matter about that. You don't have negative distance, okay? You do not have negative distances, and do not argue with me on that. You have negative displacements, physics people, but you do not have negative distances. Distance is the absolute value of displacement, you physics people, and I will correct you a lot, because I know physics pretty well. But distance is never negative, okay? It is the absolute value of displacement, and in physics, when you get into physics, the only time distance is negative is when you're talking about displacement, and that's because that negative just tells you which direction you're moving. Okay, that's all it is, it's a vector. All right, so z is equal to the square root of x squared plus y squared. Are you with me? All right, now, you guys were right. This has a y in it. That's a problem. And you never, if it's one you don't know, and you don't, let me say it again. If it's one you don't know, I don't know dy dt, and if it's one you're not trying to find, you've got to get rid of it. Because it's going to cause a problem. Now, before you say anything, so I don't want dy dt. And some of you are like, well, I don't have it. You're going to have it in a second. Because step 3 is going to be use chain rule, implicitly differentiate both sides of the equation with respect to time. And as soon as you start doing that, you're going to get a dz dt, you're going to get a dx dt, but at some point you're going to have to do, when you get into this chain rule over here, you're going to eventually get to y and you're going to have a dy dt. Because every variable in this equation has to be done implicitly because it's done with respect to time. So you have to remember to use chain rule with it. Just like we did implicit differentiation with y, we had to always remember to multiply by dy dx because it was done with respect to x. Since this is done with respect to time, the only variable we wouldn't have to do implicitly is time, but time doesn't even show up. Time is really just relative to the variables. Okay, whenever this point starts moving. Well, we're not going to talk about time specifically, so it's going to be, all right, where was the point initially? What was the original x and original y value? That'll be our time. That'll be what's relative to time, okay? Not actually talking about time itself. So do you understand that we need to get rid of y? And I don't want to take the derivative until I get rid of it. Can anybody tell me how I can get rid of y now?
Substitute x squared plus y.
That's the key. you're going to be given something in the equation that somehow relates that variable you don't need to a variable that you do need. And right there's the key. We know what y is. You're going to rewrite y in terms of x. Because if I do that, I am interested in x. I know x. That's a good thing. So if I had all x's, that'd be okay, because if I get a dx dt, that's fine, because I know that one. And I definitely want dz dt in there, because that's the one I'm trying to find. So does everybody understand? I need to get rid of y, and this right here relates y to x, so I can use this secondary equation, if you will, and replace y with what? That's it. And they'll always give you something to counteract that. Okay, problem. They'll always give you something there. They'll throw a bone at you and say, hey, I'm going to give you something so that variable you don't want and you don't want in your derivative part, you'll be able to get rid of it because I'll give you something that'll allow you to get rid of it. Okay? And sometimes you have to find it, but it'll be there, trust me. All right, so we got square root of x squared plus y is x squared plus 1, so we're going to put x squared plus 1 quantity squared. Now, I've got a z, I've got an x. Looks like to me I'm ready to take the derivative, or am I? Should I take the derivative right now?
No.
What should you do?
Right.
Please simplify it. Okay, so we're going to have z is equal to, rewrite the problem first before you take the derivative. We always have that rewrite step. So it's the square root of, let's do this, we got an x squared, somebody FOIL this for me. What would that be FOILed? X to the 4th plus what? 2x squared plus 1. So we got x to the 4th, let's write that in. X to the 4th plus 2x squared plus 1. So when you add everything underneath the parentheses here, what are you going to end up with? X to the 4th plus 3x squared plus 1. There it is. There's our equation that relates z and x now. And there's no y in it. I got rid of the y. I didn't want the y. I wasn't interested in the y. I don't need to find the y. So now we can go through and do step 3. Use the chain rule and implicitly differentiate both sides of the equation with respect to time. So let's get to z first. What's the derivative of z? 1 times dz dt. Question, Abby? Question, what now? Let's see, x to the 4th plus 2x squared plus 1. You got x to the 4th, 2x squared plus x squared is 3x squared, and then plus 1. That good? You can put it to the 1/2. That's fine. If you want to put x to the 4th plus 3x squared plus 1 to the 1/2 power, because we can't do the derivative of square roots unless they are powers anyways. I was just thinking of it as a 1/2 power anyways. So when I differentiate, let's go to the right side now, using chain rule. What is it going to look like? 1/2 times to the 8 times 4x to the 3rd plus times, this is the part people forget. Since we're doing with respect to time, we got to do every variable implicitly. There it is. You need that dx dt also. We will in a second. You need to represent it first, and then we will change it, because they will give you points for that. All right, after we've completed step 3, the rest just falls right out. In fact, Jake didn't even need me to tell him what to do in the next step. He's just like, can we go and substitute? Yes, we're going to. Because we're going to solve, because the goal is to find what? dz dt. So any variables that we know, any rates that we know, we want to plug in and get as simple as possible.
Are we just lucky here that z was the only variable on the left?
We are lucky this time. Now, a lot of times these, because of the geometry formulas, you have one variable is already solved for.
Yeah.
So a lot of times it's just going to be one variable on one side. The other side's going to have a bunch. All right, he is right. We're going to replace dx dt with what? 2. So let's do that now. That's a 2. I'm going to replace that with a 2. There it is. What happens at 2 and that 1/2 then? Cancel. So that 2 and that 1/2 will cancel. So we're going to end up with 4x cubed plus 6x all over the square root of x to the 4th plus 3x squared plus 1. And you don't have to put the square. You can put the 1/2 power. That's fine too. Now, let me tell you what you just found. This is pretty magical. You now have a formula that you can plug into Java and robotics that would calculate at any moment that moving point on that graph, the distance as it changes. So you can calculate that distance at every x value.
Yeah, but where's time? Aren't we solving for distance?
Well, there is no time because time is not really relevant here. We have time. We know time passes. The time passes based on that point moving, and that point is an x and y. So how are we going to measure time? Well, we'd have to have a starting point. So let's say the point started at 1, it'd be 1, let's see, x squared plus 1, 2. Let's say it started at 1, 2. So that's where you measure from time. So your time is x equals 1 and y equals 2 is your t equals 0. You don't really have a time variable. Your x and y variable represent the time. So that's why you have to set a starting point. So if you set the starting point to be the point 1, 2, you're saying, okay, that's time 0. So now as you move, as the point moves, whatever those new x values are, tells you new moments in time. Because you know it's moved away from that original point. That's the problem. We won't be able to keep up with the total elapsed time because it might go back on top of itself and all that good stuff. So I don't know if we'll ever know the exact time, but we know relative to time, the x and y value as it moves, we know that it's moving throughout time. Okay? So time's kind of a weird thing. It's kind of it's there. It's just like in 4 dimensions is easy to visualize if you just add time to it. You've got x, y, z. Your 4 dimensions. You've got length. You've got height. You've got width. 4th dimension is really time, but how do you visualize that? Not hard, right?
Is that movie, The Astronaut? No. Were they? Huh?
Interstellar.
Yeah.
Kind of the same thing. So here's what this is telling you, though. This is telling you the rate of change for distance with respect to time is calculated based on this equation. So this would calculate at any moment. Now the moments are going to be where the point's located. So for example, if I wanted to know when the point gets to x equals 2. So when the point gets to x equals 2. So that point would be the point 2 squared is 4, 2, 5. It's y equals x squared plus 1. That's how I'm getting that. And 2 squared is 4, 4 plus 1, 5. So at x equals 2, could you figure out at that moment how fast the distance between the origin and that point is? At that moment, you can figure out how fast it's moving. All you would do is plug in what? 2. You plug 2 in and you figure it out. So let's do it real quick. 2 cubed is what? 8 times 2 is what? 8 times 4 is what? 32. 32 plus 12 is what? 44 divided by, let's see, 2 to the 4th. 16 plus 12, 28, root 29. So you would say at that moment, when the point gets to x equals 2, the distance between that point and the origin is changing at a rate of 44 divided by root 29, and that doesn't really make a lot of sense, so we'd probably use a decimal. What's 44 divided by root 29? So you'd say about 8.17, and we don't even have units, so we'd say centimeters per what? So at that moment, the distance between that point and the origin is changing at a rate of 8.1 centimeters per second at that moment. Okay? And you can calculate it for any value. And that's where we're eventually going with this. Every question is going to give you a moment in time that they actually want you to calculate the rate of change for. This problem they did. They just had to calculate it for all x values. So when you found the rate of change for the distance with respect to time, you came up with a formula that calculated it for any point. So you could calculate the rate of change at any moment. Now the next problem is they're always going to nail it down. And I'm going to tell you on the AP 10, they always nail it down to a specific moment. And so that's what we're going to look at next. So you get a feel for how we do this? Okay, it's going to take a couple problems. You ain't going to get it on problem 1 and be like, woo, I got it, related rate, sweet. Okay, just like simple power rule. No. Don't worry about that. Okay, we're going to have to do and expose you to quite a few problems to be able to get it. All right, so here we go. That's my introduction. Let me pause that. Related rate part 1.